Up next, we've got Armen Tokadjian from USC, who's going to be talking about tides on exoplanets and exomoons.
All right, can you guys see this slide?
Yep, looks good.
Okay.
You see the timer okay?
Yeah, I can see the timer.
Okay.
All right, thank you, Paul. So hi, everyone. My name is Armen. I am a third-year grad student at USC, and I'm working with Anthony Perot at the Carnegie Observatories. So today I'm going to tell you about a recent paper we submitted that has been accepted by the Astronomical Journal, and it's entitled Impact of Tides on the Potential for Exoplanets to Host Exomoons. So we can jump right in. So there are over 4,000 exoplanets that have been discovered, and yet there has been no confirmed exomoon case. So there is one possible detection, which I'll get into later on, around Kepler 1625b. When we look at our own solar system, moons, there are plenty of moons around the planets in our solar system. So if extra solar systems are anything like our own solar system, we expect that there should be many exomoons out there, and it's just a matter of knowing where to look and finding them. So why exomoons? Well, probably the biggest reason is a moon may be necessary for life to develop on a planet. And there are several reasons for this. One is that a moon can help stabilize a planet's obliquity. And as you can see by this graphic here, the Earth's tilt varies only by a couple degrees. And without the moon, it might vary by more than like 80 degrees. Secondly, a moon can prevent a planet from having one side facing the star at all times. A moon can also help drive tidal heating within a planet. So it can help push tectonic activity like a cycle of important gases. And it can also help the dynamo effect to preserve the magnetic field. And that could help preserve the atmosphere as well. So for gas giants planets that don't have a solid surface, we may look for the moon itself for life. So before getting into tides, there is a certain range of distances a moon can orbit around the planet. We have a minimum distance. Within this distance, a moon is subject to tidal forces by the planet. So it can be tidally ripped apart or even crash into the planet if it comes in too close. This minimum distance is given by the ratio of the planet mass to the moon's density. There's also this outer limit. If a moon goes past this outer limit, it is subject to being lost to the star. And this is given by the ratio of planet mass to star mass times the distance the planet is from the star. So here's an example for the Earth. If the moon should come in too close, about 4% of its current distance, it'll be tidally disrupted. If it goes out too far, 2 times its current distance, then it'll be lost to the sun. Okay, so what causes the moon to go in and out of its orbit? Well, this is due to tidal lag. So we know as the moon pulls on the Earth, for example, it's going to create 2 bulges like this. But this is not what the picture looks like because it takes some time for the planet to respond to the gravitational effect of the moon. So in reality, what happens is the Earth will rotate a little and then the bulge will occur. And this is what tidal lag is. So we have this angle delta that defines this angle between the bulge and the moon. Now the moon will pull on this bulge, slowing down the Earth, and it's going to get pushed away as a result. Now eventually the moon and the Earth will be tidally locked. And at this point, there will be no more torque due to the moon on the Earth because now the bulge will align with the moon. At this point, however, the sun's effect becomes dominant. The sun will continue to slow down the Earth such that the Earth will now lag behind the moon. And at this point, the moon's going to speed up the Earth and the opposite effect's going to happen with the moon coming in. And this is going to keep happening until the moon eventually crashes down and gets tidally disrupted by the Earth. So to get the time scales, we need to look at some time lag and phase lag models. We have the first one, the CTL model, or the constant time lag model. This says that it takes a certain amount of time for a planet to respond to tidal effects. So for rocky planets, it'll be around 638 seconds. The torque in this model is given by this time lag tau times the difference between the orbital frequency of the moon and the spin frequency of the planet. So as these numbers get closer together, the torque will go lower and lower over time. Next, we have the CPL, or constant phase lag model. In this model, this angle that I showed you earlier is going to be constant rather than the time it takes for the bulge to appear. This is parameterized by the quality factor Q, which is low for highly dissipative planets like the Earth and higher for lower dissipative planets like gas giants. Now, the torque in this model is actually constant. It's dependent on the sign between the difference between the frequencies. And because this one's constant and this one is diminishing over time, we expect the CPL model to give shorter timescales overall. So this is an example of running the CPL and CTL model on the Earth-Moon system. We have on the y-axis the separation between the Earth and the Moon, and then time on the x-axis. I've also shown you the maximum and minimum distance the Moon can orbit around the Earth. So I'm looking at the CPL model, for example. We can see that the Moon is being pushed away now, and it's going to be tidally locked around here after 6 gig years. Then the Moon's going to start falling in, and it's going to be tidally disrupted after 68 gig years. The CTL model, as expected, has much longer timescales. Now, an important thing to note is that even though they quantitatively differ significantly, these two models qualitatively give the same results. Okay, so to apply this to real exoplanet systems, we need to make a number of assumptions. We choose a moon that's the same size as our moon, and we place that moon in between the minimum and maximum distance that it can orbit the planet. We assume that the planet is spinning at the same rate that it is orbiting its star. We classify the planets by radius and density into 3 groups. We have the rocky Earth-like planets, the Neptune-like planets, and the Jupiter-like planets, each with their own quality factor Q and time lag tau. And we are extending the work by Martinez, Rodriguez et al. To a broader range of planets, and we're doing the full integration to see how long known exoplanets can hold on to an exomoon. And we pull the exoplanet list from the NASA Exoplanet Archive. Okay, so here's the first of our results. So on the y-axis, we have how long the moon can last around the planet, and we have the flux that the planet receives on the x-axis. We have highlighted the habitable zone by these vertical lines, and we have 1 gigayear as a thick horizontal line. The color of each of these points represents the ultimate fate of the moon around the planet. So green means that the moon is going to last over 15 gigayears. Blue means the moon is going to be disrupted after a certain amount of time, and red means it's going to be lost to the star. Circle represents planets that we're treating strictly as rocky planets, whereas triangle means that we're not sure whether it's rocky-like or Neptune-like. So we're going to assume it's rocky here, and then later on we're also going to assume it's Neptune-like and run the integrations. So really what we're interested in most is this zone right here, the square made by the habitable zone and 1 gigayear. These are the planets that can keep a moon for over 1 gigayear and are in the habitable zone in their system. Next, we have the CPL model on the Neptune-like planets. And because Neptunes are a lot less dissipative, as expected, they have a lot longer timescales for holding moons. So we see there's plenty of moons here in this zone for Neptunes. Finally, we have the Jupiter results. And Jupiters are the least dissipative of all, so they have the most. Like I have hundreds of planets actually here that can hold on to a moon for longer than a gigayear. Okay, so in our paper, we outline several important cases, and I'm going to share a few of those with you today. So the first is Kepler 1638b. This planet is interesting because it has a radius that places it right in the middle of the Fulton Gap. So you've seen this plot a few times yesterday. And this planet's radius falls right in between the super Earths on the left side and the sub-Neptunes on the right side. So we're not entirely sure if it's rocky-like or Neptune-like. And if it's rocky, actually, the moon will last significantly less time than it will if it's Neptune-like. So if a moon is actually found orbiting this planet, it might tell us something about the composition. Then we have Kepler 1625b, and this is the actual exomoon candidate. And the Jupiter plot I showed you earlier actually had this planet, and this is this planet right here. So we can see that Kepler 1625b has the potential to hold a moon for over 15 gigayears. However, our assumption was that this is an Earth's moon size moon, when in reality, this exomoon is thought to be Neptune sized. So what we did was we ran our full integrations again, taking this into account, and we had this plot. So this is a plot of period in days versus time. We have the period of the planet orbiting the star in red, the moon orbiting the planet in blue, and then the spin period of the planet in green. So we've tried this for various initial spin periods, and we find that in all three cases, the system is very stable. So that can be seen by the moon's orbit around the planet. It doesn't change much at all. So we conclude that the moon would be stable under tidal effects, even if it's Neptune sized. Okay, so to conclude, as I've shown you, moon may be a significant aspect of a planet's habitability. In our paper, we outlined 36 specific exoplanets that are in the habitable zone and can hold a moon for over a gigayear. And I've showed you 2 examples of that. And there's a variety of things we can do for future work. We can look at multi-planet systems, or I have to use an n-body integrator for that. And consider varying other variables, because there are so many parameters in this work, like, for example, varying the initial planet spin rate. And we can also look into additional effects like resonances, looking at eccentricity changes, etc. So that's all I have for you today. I think I finished a little bit early. I'll take any questions now. Thank you.
All right, thanks so much, Armen. It's really interesting stuff. Reminder that I'm looking for questions in the Slack channel. And while I'm waiting on that, I will use the chair's privilege to ask one. Armen, I'm curious, how confident are we? You know, you listed Q values for the Earth and Neptune and Jupiter. But if I have a super Earth that is maybe a more kind of a rocky body with a thicker hydrogen helium envelope, how confident are we in our knowledge of those Q values?
Yeah, so the Q value I took was specifically for the Earth. So that is assuming the same composition as the Earth. So you're right, super Earth with that kind of structure will have probably a much higher Q. So that's another option we're looking at when we're doing future work. So varying the Q value to make it more accurate for different kinds of planets.
All right. I've got a question here from Jason Wong, who says, how far away are these moons from their planets typically in your simulations? Is there a preferred separation?
So do you mean how far the exoplanets are from their star? Is that the question?
No, it says how far away are the moons from their planets?
Okay, so for that, I'm calculating the minimum distance it can orbit and the maximum, and I'm placing the moon to start right in between those two extremes.
All right, and it looks like I'm getting another question. I'm allowing time for typing here. I guess this is kind of like waiting for the question asker to walk to the microphone. Question comes in, is the paucity of moons surprising?
The
small number of moons that you're finding are stable, is that surprising to you?
No, actually, because especially for the planets that are close in, the outer range and the inner range are actually pretty limited. So the maximum and minimum distance are pretty close together, especially for an inner planet. So
okay.
Because
I'm gonna stop you real quick because I misinterpreted the question. I think the
Okay.
question was that are you surprised, given your results, that only one exomoon candidate has been found?
Oh, well, I'm not surprised that one exomoon candidate is found because, I mean, it's difficult enough to find exoplanets, let alone their moons. So that the techniques of finding them need to be more fine-tuned. But I think there are plenty of moons out there, and as soon as we have the technology for it, we're going to find plenty of them.
Okay, so we have a prediction. Another question was come in. Do we have time here, Colby?
30 seconds.
Okay, quickly, how did you decide on the spin rate for the planets in your simulations?
Yeah, so I chose the initial spin rate to be the same as the orbital rate, and that's actually the most conservative approach. So I tried it for different kinds of spin rates, and the one where the spin rate is equal to the orbital rate, it has actually the shortest time scale of all the time scales, as long as the moon doesn't get pushed far enough early on. So I took the conservative approach in that.
All right. Well, thanks again, Armen.
Thank you very much.
Let's try to stay on schedule here. Do we have Max?